So now it is to Fabiano, I think. Fabiano.
Yeah, thank you very much, Celine, and thank you for everybody that watching me. My name is Fabiano Ribeiro. I am a professor at Brazil at the Universidade Federal de Lavras, and I'd like to talk to you about the transversal and longitudinal scale in cities. Specifically, transversal scale means that all the scaling properties that we have observed recently or the past decades about systems of cities. And longitudinal means the same properties of scaling, but at the level of this individual city. And what I'll try to present is a study that I used more than 5,000 Brazilian municipality data, and I try to present you a model to try to explain my results. And at the end, I'd like to say if the individual city is or is not a small version of a system of cities. And today we live in a very special moment in the history because today, in the same way that a biologist can see the biological tissue by the lens of a microscope, we can see your city by the huge amount of data and the use of the very specific kind of softwares. And with this huge amount of data, we can, for example, extract some information about the cities and, for example, how the amenities are distributed around the city and how if there is or there is not some kind of patterns that can be observed in many kinds of cities around the world. And we've used this huge amount of data. We already have observed that some patterns apparently do not depend on the history, culture, or geography of the city. And one example is the scaling properties. For example, here I have the GDP as a function of the population for two very different kind of countries, that the USA and Brazil. Here, every point here in this graph represents one city of these two countries. And besides, these two countries are very different in terms of economy. Apparently, the scaling properties that is characterized by this blue and the green line here in this log graph, the slope of these two lines is approximately the same. That is what we call now the beta parameter, that is superlinear. That means that when you increase the size of the city, you more than increase the gross domestic product of every city in these systems. That means that you have an increased return to scale when you increase the size of the city. This is so robust that when you, here you can see the chaotic movement of the cities. And beside this chaotic movement, the red line that represented the scaling of these systems of cities maintain approximately constant. The slope is approximately constant. Beside all the erratic movement, apparently erratic movement of the cities. And however, there's another kinds of urban variables that also have a scaling property, but instead you have a sublinear behavior. That's the case of infrastructure kind of variables. For example, here you have the number of petrol stations that present this sublinearity. That means that when you increase the size of the city, you decrease the per capita number of this infrastructure variable. This also presents this approximately the same value no matter the country. Here we have 4 different countries, and the beta related to infrastructure is apparently the same. But why this kind of scaling emerge? What the origin of these scaling properties? And what I and my colleagues try to do to try to understand this kind of properties, this kind of urban properties, is to try to represent the socioeconomic hazard output of the interaction between the people that lives in the city. For example, imagine here you have a person that lives in this, imagine that here you have a person that lives in one part of city, and suppose that this guy interacts with the person that lives in this part of the city. And the number of interaction that this guy have with all the person that live in this part of the city, we will consider by hypothesis that decay with the distance. And the model that we have studied in the last years with my colleagues is to try to say that the socioeconomic is an output of, is a consequence of the interaction between the people, and this interaction decay with the distance. That means that we hypothesize that the probability of interaction between two people decay with this formula. And here we have a parameter of the model that I will call gamma, and this parameter measures the range of interaction between the people. And this hypothesis has some empirical evidence to support. And here we have the distribution of physical distance of Facebook contacts that is apparently is in agreement with the hypothesis, apparently decay with the distance according with the power law. And here we have also the distribution of male distance, and also it is well fitted by this power law. And with this empirical evidence, we can infer some numerical value for this parameter that measure the interaction range put in the model. That is around 1 and 1.5. And also, I think that we consider the spatial distribution of the city. In our model, we consider that the structure formed by the cities obey a fractal structures, and here you have the histogram that represents the number of a set of cities and his respective fractal dimension of the city. And you can see here for this specific set of city, you have a fractal dimension around 1.7. And if the city is well represented by the fractal structure, you can say that the density of the city can be right in terms of this equation here. With this consideration, we can say that here you have the probability of interaction, here you have the density of individuals of a specific part of the city. So these terms here represent the number of interaction that one individual have with a person that live at a distance r. When I integrate all these parameters here, we have all the number of interaction that one specific city, one specific individual have. And then when we multiply it by n, we have all the number of interaction that you have in your city. And by hypothesis, we consider that the socioeconomic output is directly correlated with the number of interaction. And then when I compute this equation here, emerge two kinds of properties of the model. For example, when you have short range interaction, we have a linear relation between the socioeconomic and the population size. And when you have, now we need to say what means short range? What means short? Short here represent that the gamma is greater than the fractal dimension of the city. And otherwise, when you have gamma smaller than the fractal dimension, that means that you have in the long range interaction regime, and now you emerge the nonlinearity that you have observed in the empirical data. And in addition, we can also write the beta, the scaling exponent, has a function of the geometrical property of the city. That is beta has a function of gamma and the f. And what is interesting about this result is that the nonlinearity of the scaling property of the city emerge as a consequence of the long-range kind of interaction between the people. That means that if you have a city that have only people that interact only with the near person, not with the city as a whole, you don't have emergence of scaling properties. That is an interesting result of our models. And you can also compute the infrastructure using the same idea of the decay of the distance. You can simulate, for example, the number of amenities in the city. Here, my city is generated by a DLA algorithm, and the city is the small ball, small circles, and the triangle is the facilities. And if you wait enough, the number of facilities will be in equilibrium. here we have a competition between the facilities. And if you do the same simulation for different size of the city, what you can see here is that when you increase the size of the population, you decrease the per capita number of amenities. And also the gamma that measures the interaction range also play a very important role here in the economy of scale here in this model. Okay, up to now, I'm talking about the transversal scaling, the scaling in the system of city. But what about the scaling at the level of an individual city? Does the individual city have the same properties of the systems of city? The first thing that I note here is that when I plot the trajectory of the city here, you can see that the slope of the individual city is apparently greater than the slope of the transversal scale, the slope of the scale of the cities. And here you can see that this trajectory you put in the appropriate way, put all the trajectory in the same area, you can see that in fact the slope of the individual city is greater than the slope of the transversal scale, and the slope of the scale, the system of city, but it's distributed around a mean value. But the mean value here is very different from the value that we have observed in the transversal scaling. But what happened? Here we have, let me, I don't know if I can see this formula here, but I can take it off this. And the idea here is to try to understand the movement of the city in the phase, the plan phase that have the x like a n, and here you have the A, the socioeconomic output, and here you have a vector field that move the city from this point to this another point here in time. And this vector I know, and this vector I also know, but I don't know about this two vector here. The vector here, I can assume that is an outcome of the scaling property. That means that is proportional to this change here related with the population, erasing to the exponent. And if I know this by subtraction, I can infer this external factor here. This vector represents all the externality that act in one particular city. Externality means that all the things that don't have nothing to do with the scaling properties. And when I sum all this vector here, I can write the individual beta as a function of the transversal beta plus this sum here that have an external component, and also a term that depends of the growth rate of the city. And then when I rewrite the histogram that I previously present to you, but now taking off this factor, the external factor here, we can see that from GDP, in fact, the beta is distributed around the transversal beta. That suggests that maybe this this method can be a way to understand that the individual beta is approximately the same, is compatible with the transversal beta. However, when I do this for other kinds of variables, for example, the Walter network length, in fact, when I decompose the data, the mean beta of the individual cities become very different from the beta of the transversal beta. So that means that for some variables, this methodology works, but on other kinds of variables, this methodology doesn't work. And the other point that promotes some inconsistency of the data is that when you have a city that have a very small growth rate, for example, I represent here by the letter B, when you have a growth rate very small, that implies that the beta is very large. That's inconsistent because we have a very large number value of these betas, and you have an inconsistency. What I can do to try to fix that is to remove from the statistics all the cities that have a growth rate is smaller than the given value. When I do that, the mean value of the individual beta approach to the transversal beta. So that is all for that is my results. And as a conclusion, I can say that I have proposed a model to explain Ribeiro scaling, and we realized that individual cities are a small version of a set of cities when we have absence of externalities. Externality means that all the things that have nothing to do with the scaling properties, and also when we have cities that have growth rates sufficiently large. Thank you very much. That is my collaborators here, and that is the support. Thank you for the support, and thank you very much for all the audiences. And I'm look forward to see your question. Thank you very much.
So thank you. Yes, it was a wonderful presentation. Thank you very much. Are there any questions?
I think that I need to stop my share now, no?
Yeah.
Now the people.
Yeah, it's okay. Okay. So is there any question? Maybe I've got one. So the alpha, I think it is what we call the friction of distance, right? Because it is how far the interaction are break or by the distance. So it is what geographers we call the friction of distance in the gravitation model, right? And in a way, so it is linked to the shape of the city and the way the city is planned and organized. And so is there now a relation between the fractal dimension and this friction of distance? Because you compare them, but are they not linked in a way?
Yeah, that's in fact, that is the question that I'm looking for now, because in fact, the model say about the ratio between this range of interaction and the fractal dimension of the city. In some way, the model says that this value of this fraction is important. But the problem that I'm faced now is that I can explain the fractal dimension. It's a quantity that I can understand in some way. But the gamma, the parameter that measures the interaction range of the people, I can say nothing about. It's how can I say, it imposed by hand in the model. And I think that that is a very interesting point to explore, because gammas reflect some humanity characteristics. For example, why I want to move 10 meters or 1 kilometer to buy something, but I don't want to walk 10 kilometers to buy something. I think that these parameters reflect this human decision that define how long I want to walk to buy something. Mm-hmm. How long I want to drive to buy something. I don't know how to do that. That is a point that.
But you know, it exists a lot of geographers work on that for so long time. The gravitation model was proposed in the 19th century, and during it is travel time budget as it is said in the chat, and so you can compare different activities or different services, and you have the way the people they are ready to take for a certain type of services or shop and so on. And when you see also the distribution of different services, for example, the bakeries or pharmacy or doctors, it indicates how long the people they are ready to move also. So this is why this alpha, so the friction of distance, is linked to the shape of city. because when the things are less dense, you are obliged to move more, and you know, and yeah. So there is something here, I think, and you can find many things in the. Do you know Tobler? Tobler,
Nope.
Walter Tobler, Tobler. He is very famous in geography, and he formalized this gravitation model in geography, and you will find many things in his work. But I think that, of course, with the new tools, you go much further, geographers. But in a way, geographers and all the empirical studies they made could be useful for you.